Hi there, welcome to my presentation on the Mima Mounds. We're looking at how the cryptobiotic crust was affected by a fire that went across them. We'll get started. Over here in our introduction, we talk about September of 2020, the Evans Canyon fire partially burned areas on the Umtanum Ridge south of Ellensburg, Washington. So we looked at this burn area and there were Mima Mounds that were scattered across it, which is a geologic formation composed of piles of silt about a meter tall and a wide variety of sizes from 5 to 50 meters across. We just conducted a pilot study to see any potential relationships between the fire and the biological soil crust. We also call it the BSC, the coverage on mounds and intermounds. BSC is a layer composed of small organisms like algae and mosses, and it forms on top of soils in our climate. If you look over on the right and over here, we have some examples of that. You can kind of see the algae and the mosses and those like greens and browns and how it just kind of looks really crunchy and stuff like that. That's what our biological soil crust looks like. So going back to our introduction over here, we were interested in this because the presence of BSC has been shown to be a strong influence on the health of soils and plant communities in the area. So we wanted to look at the relationship between the BSC and the burn patterns. And we just wanted to see what relationships there might be between the fire and the BSC, and that might guide future studies and inform decisions about fire prevention, management, restoration to these areas. So if you look right below it, you'll see the site map that we chose. I'll talk about that a bit more in a minute when we get to the methods. So first, what we were thinking we might find out there, so our hypotheses. Our first one was that the biological soil crust, or BSC coverage, would be greater on the mound tops than the intermounds, and that the biological soil crust would be disproportionately affected by fire across the mounds and intermounds, so that we'd see a difference between how it was affected on the top and on the bottoms, or intermounds. So our methods for doing that, we're going to pop back up to the site map. The first thing was we used satellite and drone photos to find 5 matching pairs of burnt and unburnt mounds and intermounds of relatively similar sizes. So if you look up here, this red portion shows where the fire went through, and the not red portion is mounds where there was not fire going through. And we tried to match them up with other mounds. So you can see almost this big blob within the red where that yellow pin is pointing. That is one mound that we paired with this other big blob mound, I believe right here. There's a few big blob mounds we paired, so there's like a kind of more blobby one here, big blobby one up here. And we just really tried to pair them 1-to-1 as best we could, just for the sake of eliminating any variance based on maybe mound size or anything else that could be introduced by that. Going on for equipment, we used this frame that's over here, 1 meter by 1/4 meter quadrat frame, and we used a camera with a tripod to take pictures. We then uploaded those pictures into a program called SketchandCalc, and you see this is the photo without the frame, and this is it with the software that we used. So SketchandCalc essentially lets us take the inside of this frame and then throws a grid over it, and then lets us draw where we see the crust at and make basically these blobs. All the purple spots are where we saw crust at, and then it looks at that, loads that information in, and then it spits back a percent of how much of that area did we just look at that had biological soil crust on it. And of these pictures, we took 4 on each mound on the north, south, east, and west faces of the mounds, just to get a good spread of data points. And so that pretty much takes over our methods. Going on to what we found with those methods, so our results. Here are the graphs that we kind of used to show those results. So hopping right in, our first hypothesis, so BSC coverage greater on mound tops than intermounds, shown to be invalid. So we can kind of look over here and see that the intermounds actually had more overall than the other places. So for example, this is our highest column. This is our unburnt intermound. So this is what it is just naturally like. without any fire, anything, this is where the most unburnt, or where the most BSC just happens to be, which was surprising to us, but we'll go more into that in the conclusions. And then, yeah, this talks a bit more about it. And then with our unburnt mounds, yeah, lowest BSC, yeah, unburnt mound tops had the lowest BSC cover and greatest variance. So we have our unburnt mounds right here. So this is just regular mounds, and they had the lowest, which was just really interesting to us, but we continue. Then we have the, we did a two-tail Fisher test, gave us a P number of 0.0138, and just kind of shows relating factors, and to sum it up, it supports the second hypothesis, which was showing that BSCs are disproportionately affected across mounds and across intermounds. So looking at this, you can see how these numbers aren't the same. Like, we look at our unburnt mounds and we look, or unburnt intermounds, and we look at our burnt intermounds. Wait, it's the red one here. And there's a huge difference. Same for our burnt mounds and our unburnt mounds. These are very just contrasting numbers. They're not very similar. You can kind of see them all represented here as well. You see this huge one for the unburnt intermounds and this kind of smaller one for the burnt intermounds, larger one for burnt mounds, and smaller one for unburnt mounds. So these numbers are just different. We found that they were not the same for each set, that they were affected by the fire going through on all levels. So going into discussions and conclusions about those things that we just found. So we found that, yeah, their mounds and intermounds are burned disproportionately, but some things that we found about that. So going into the hypothesis we just kind of mentioned earlier, results showed that the first hypothesis rejected. There was not greater BSC on top of the mounds, but rather in between the mounds, which we found interesting, thinking that the silty environment would be better for the growth and the more rocky intermounds would be less good for growth, but that was not shown. Our second hypothesis, though, was found to be true because of the difference between the percent of biological soil crust on unburnt and burnt areas that were correlated. However, some interesting points that we found. So there was sufficient data recorded on the unburnt mounds. The problem we were finding was the vegetative cover. There was a bit of a time restriction, but mainly the vegetative cover. Any spot where it was completely covered in shrubbery or grasses, we couldn't see the biological soil crust, so we couldn't measure the percent of it at that area. And this proves the problem because either underneath it, there could be a thriving biological soil crust that we just can't see. Maybe this area is so fertile, it has so much shrubbery and vegetation, and underneath it there is an equally thriving biological soil crust that's just not getting represented in our data. Or it could be the other way. Maybe those plants choke out the biological soil crust and make it so it can't really thrive there. Either way, we were unable to record it because of the vegetative cover. So some suggestions for future studies that we thought of were using different methods to remove that barrier, such as using LiDAR, removing excess vegetation, selection of mounds with non-obscuring vegetation, though you might be missing some points when you do that, or even just studying at different times of the year. And then, yeah, that's for the most part a lot of the things that we found. Some things that we were mentioning as well that we thought were interesting and might be points that change things or not, but there was some variation on the rock rings, such as rock size, circle thickness, and presence on each mound. So at the bottoms of these mounds there was often rock rings, and we could see different variations within them, and those were in our intermound spaces. So looking at how different types of intermounds and rock rings that exist in the intermound spaces are affecting data would be interesting to look at as well. That is all. Thank you for coming to my presentation.